Welcome to Module 3, Discrete Random Variables. This is our first look at the concept of a random variable, and these are not random variables that are very coy or secretive. Discrete means something else. This is not discrete. EET, this is ETE. All right, random variables. What are random variables? There's a kind of a technical definition and a more intuitive definition. So a little more technically, it's a function that assigns a value to each of the outcomes of a random experiment. So numerical value. So random variables only take numerical values. They're not going to be categorical, okay? The only way you could do some categorical is like category 0, category 1, category 2, something like that. But it has to be numerical. But in principle, you can kind of think of it like a variable x or y that has a different value, or it takes a random value each time you observe it. So it's like behind this card. Every time you flip it over, the value is just flipping through all the random possibilities. Every time you look at it, it freezes with whatever value it's taken. And it takes these different values with certain probabilities. So one simple example would be to assign the random variable x to be equal to 1 if you flip a heads and equal to 0 if you flip a tails. That would be one way of making a random variable. So you can see in that sense, it is assigning numerical values to outcomes. So the outcome heads isn't numerical, but we give it a numerical value of 1, and that way we've turned it into a random variable. Random variables, when they're discrete, that means that they take specific values with positive probability. So you can think in principle, or usually it's going to be integer values. So the variable x maybe takes the value 0, 1, 2, 3, 4, 5, 6, and so forth with certain probability. That's a discrete random variable. We will look at continuous random variables in the next module. Continuous random variables can take any value along an interval, and they have to be treated a little bit differently, so we'll talk about them next module. So the probability mass function, sometimes called a probability distribution function. I'm avoiding that term because of the confusion with its abbreviation PDF. That can be confused with a different abbreviation. So I'm going to call this a probability mass function, because to me, I think it helps to think of it in terms of probability having weight or mass. And so the mass function takes our one block of probability that equals one mass, 1 unit of mass, and we divide it up among all of the possibilities. Okay, that's a way of assigning each outcome or each value that the random variable can take a certain amount of probability mass. So, of course, each probability has to be somewhere from 0 to 1. Now, if one of the outcomes is not possible, then its probability is going to be 0. That's possible. If the random variable only has one value that it takes, its probability is going to be 1. That's going to actually be a constant variable. All right, it's a constant. But generally speaking, or I should say usually, these probabilities will be between 0 and 1. And of course, because we've assigned the entire 1 unit of probability mass, if you add up all of these probabilities, they need to add up to 1 exactly. So here's an example. This random variable x takes the value 0 with probability 0.23, takes the value 1 with probability 0.17, it takes the probability 2 with probability 0.55, and the value 3 with probability 0.05. So you can see most of the time it's going to be a 2, sometimes it's a 0, and less often it will be a 1, and very, very, very seldomly it will be a 3. So that's the idea. Now the first kind of property of a random variable that's important to look at is the expected value. Now, it doesn't mean that we expect the random variable to take this value precisely. What the expected value is, it's more of a theoretical long-term average. And that means if we were to observe this random variable again and 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 again, over and over and over and over, the average value of all of these values that it takes, the average value should be pretty close to this expected value. The terminology or the notation we use, capital E parentheses capital X, this is the notation, or sometimes we just use the Greek letter mu because the expected value is the mean of the random variable. So in terms of statistics, the population mean is the expected value. These are analogous concepts. So there's a fairly simple calculation for it if you wanted to do it by hand. What you do is you take each value that the random variable can take, you multiply it by its respective probability, and you do that for each of them, and you add up all of these products. So it's 0 times 23 plus 1 times 0.17 plus 2 times 0.55 plus 3 times 0.05. That's the expected value. So this random variable, the expected value is 1.42. So of course, this random variable never will take the value 1.42 because it's either a 1 or a 2. It's never between them. However, if we were to observe this random variable again and again and again and again and again and average out all of our observations, we should get an average that's close to 1.42. There's a principle called the law of large numbers, which says the more times you observe a random variable, the closer your sample average will be to the expected value. It should get closer and closer, in theory. And that usually is the case. The standard deviation is the next very important property. Now, I'm not mentioning the variance, but I don't have the variance on the slide, but I'll mention it. So standard deviation, it is technically the square root of the average squared deviation from the expected value mu. So what does that mean? It means what we do is we take all of the possible values this random variable could take, and you would say, okay, how far is it from the mean, or the expected value, square all of those deviations, and then you take a weighted average, and you weight all of, when you average it, the weighting is by the probabilities. So there's actually two formulas for it, but I'm going to show you the simpler formula. Now, don't feel scared. You don't have to use the formula. You can use software to calculate the standard deviation for you. I'm just showing you giving you a little bit of intuition behind it. So before that, standard deviation of x is abbreviated or notated with SD parentheses x sometimes. I often use that notation. Sometimes sigma, because that's the standard deviation of a population. That's the parameter. It's the same concept. And this formula is the square root of the expected value of x squared minus the expected value squared. Notice the difference. Having the little exponent 2 inside the parentheses makes a difference. The first expected value is we take all of the squared values that the random variable can take, all of the values, square them all, and then you find the expected value of those squared values. And the second one, we just take our expected value just like we calculated in the previous, and we square that number. Now the first value will always be slightly bigger than the second. So you're guaranteed you're going to never have a negative number. You're never taking a square root of a negative number. That's just the way the math works out. So to find the standard deviation of this random variable we just looked at, we make another column of the squared values, x squared. So when x is 0, x squared is also 0. 0 squared is 0. When x takes the value 1, x squared is 1, because 1 squared is 1. Now where it starts to change, when x takes the value 2, x squared will be a 4. And when x is a value 3, x squared is a 9. But the probabilities remain the same, because there's just this correspondence, right? X squared will take the value 9 with a probability of 0.05. Right? Because it happens precisely when x is equal to 3. So the expected value of x squared is found just by taking 0 times 0.23 plus 1 times 0.17 plus 4 times 0.55 plus 9 times 0.05. That's 2.82. Okay, that's our first value that we need. Next is the expected value of x squared. Well, we found it previously to be 1.42, so we square 1.42. We get 2.0164. So now the standard deviation of x, we have to take the square root of this difference, 2.82 minus 2.0164. First, we take that difference, comes out to be 0.8036. So the square root of 0.8036, I rounded to 4 decimal places, it's 0.8964. So that's the standard deviation of this random variable. And you can, just the same way with the statistic, you can roughly think of standard deviation as the average distance from the mean. So on average, our random variable will take a value roughly 0.89 or about 0.9 away from 1.42. That's the average deviation, average distance from the mean, roughly speaking. It's not precisely what it means, but roughly. That's the simpler understanding, even though it's not exactly correct. Now, I said I would mention variance. Variance is simply, you just don't take a square root. The variance is the standard deviation squared, just as it is with the statistic. So the thing is, the variance isn't really isn't a very useful number for us, so we're not spending time on it because it doesn't have an interpretation that's meaningful, but standard deviation does. Now let's look at some important discrete distributions. These are random variables that are very useful for modeling certain situations. So they've been named, standardized, and some of their properties have been identified. So first, a uniform distribution. A uniform distribution means that you have n values that the random variable can take, and because they're equally likely, therefore the probability of each value will be 1 over n, 1 divided by n. And a very classic example would be rolling a 6-sided die. X is the number on the top of the die after you roll it, so the 6 numbers each have a probability of 1 divided by n. Another example would be flipping a coin. If we assign the value 0 to, say, tails and 1 to a heads, then they're equally likely, so they each have a probability of 1 divided by 2, 1/2. A binomial random variable is actually, it could be thought of as extension of flipping coins. So a binomial random variable is used to model the following situation. So we have a fixed number of observations, also called trials. So we're going to say the number of trials is n. Okay, so it could be like 5 or 10 or 100, whatever. So you try some experiment a fixed number of times. Each of these trials has two possible outcomes, either a success or a failure. Think of it as heads or tails. But it doesn't mean that they're equally likely. We have a probability of success of p. So some specific probability of success on each trial. And the probability of a failure is going to be 1 minus p, also known as q. Sometimes it's called q. That helps just clean up the formulas a little bit, just call it rather than 1 minus p. But honestly, 1 minus p is pretty simple. Okay, now the trials are independent, which means whether or not one outcome is a success has no bearing on the likelihood that any of the others will be a success. So there's no memory in the process. Each outcome is completely independent and unrelated to the outcomes of the other ones. And so finally, the random variable x is the number of successes observed after n trials. That is a binomial random variable. Okay, so this is the notation that you will sometimes see. We use x with a little tilde, and I abbreviate it binom. You might see just the letter b, but it should be clear from the context. That little squiggle means x follows the distribution. So binom. And then two parameters that you need to know are n and p. You don't need to be told what q is because q is just 1 minus p. So you have to state what the two parameters are, and then the distribution is completely defined. So we have the mean, or the expected value of a binomial, is n times p. That's the one little formula that's useful. And the standard deviation is going to be square root of n times p times q, also known as n times p times 1 minus p. And as a little side note, if n is equal to 1, this is called a Bernoulli trial. That's like flipping a weighted coin one time only. Okay, the next one is the geometric distribution. A geometric random variable can be used to model the following situation. So you observe Bernoulli trials with a probability p of success. Okay, so it's like you have a weighted coin and you're just going to keep flipping it. And each trial is independent, so there's no memory in the process. Every outcome is independent of all the others. And the random variable is how many trials it takes until and including your first success. Sometimes people define a geometric distribution to be the number of trials it takes before the first success. But I'm going to use until and including the first success. So it's possible that you could flip a coin and you get a heads on the first try, or it could be the second or the third, the fourth, the fifth. But it'll never take 0 tries because you have to flip it at least once under this definition. Under the alternative definition, it could be a 0 because if you get a heads on the first try, that means there were 0 trials before the first success. So you want to be clear from the context of the problem which one you're using, but we're going to use this definition. Notation you might see x squiggle geom and the parameter p. P is the only parameter in a geometric distribution. The mean of a geometric random variable is 1 divided by p. So that's to say, on average, it should take 1 over p. So think of it like this. There are cereal boxes, and there are 5 different toys that there are. One of them is your favorite one, and you want to get that one. So every time you open a cereal box, you're going to get a random toy, but you have a 1/5 point. It's a 0.2, or let's just say 1/5 chance of getting that toy on each cereal box. So you keep trying and trying and trying. You open up cereal boxes. Well, how many cereal boxes should you expect to have to open? That would be the expected value of a geometric random variable. And so Since the probability is 1/5, the reciprocal, flip, of that is 5 over 1. So you would expect, on average, to have to open 5 boxes of cereal to get that toy that you really want. That's how you can interpret this or think about this expected value. And then this next is the formula for standard deviation in case you ever need it, but you can always look it up on Wikipedia. A Poisson random variable can be used to model this situation. So you are going to observe random events over a fixed period of time or a fixed space. For example, fixed time could be you are going to, over the course of 8 hours, an 8-hour workday, you are going to observe how many phone calls you get. Or maybe you're going to drive for a stretch of 50 miles through the woods, and you are going to observe over those 50 miles how many like dead animals, like roadkill, how much roadkill you see. So a dead animal by the side of the road is like a random event, and the fixed space is the 50 miles. Or there's a lot of different kind of examples you could think of like that, but you have a fixed amount of time or space, and you're counting how many times this random event occurs over this time. So we need the events to be occurring randomly and also independently of each other, and then the mean number of occurrences over this fixed time or space is mu. This is the one parameter of our distribution. So the Poisson takes this one parameter mu, and the nice little formula for standard deviation is it's the square root of mu. And so those are some of the important discrete random variables, and there'll be another follow-up video where I will show you how to use a calculator to calculate some probabilities for these distributions.